Today we want to do some more practice with double integrals. It's going to be describing a region and thinking about integration. Applications of multiplication are applications of integration. Integration is multiplication where one of the factors is continuously variable. When we first, sorry, what? Yep. This line will show up all the time because this is important. This is how we think about integration. When we first introduced the concept of the definite integral, we framed it in area, length times width, because it was convenient and we like to tie the graphing part to the mechanical part. So we started off doing area is equal to length times width. When length is constant over the width, all we have to do is multiply. If the length is constant over, say, some interval, then the area is just a product. Say y equals, I don't know, I need a value, k. That area is just the length times the width. We get to multiply because the length is constant for the entire width. This becomes an integration problem when length is continuously variable over the width. In the second picture, the length is continuously variable, and this turns into an integration problem. Instead of just multiplying, we integrate from A to B. The length dx. In both cases, we have area is equal to length times width, but that's just the area, taking this picture literally with area. But if on the vertical we have velocity and on the horizontal we have time, then area represents distance. If on the vertical we have acceleration, on the horizontal we have time, then the area represents velocity. If on the vertical we have work and on the horizontal we have distance, then the area represents, if on the vertical we have force and on the horizontal we have distance, then the area represents work. Any application of multiplication can be put into this framework. All we have to do is take one of the factors and make it continuously variable. Integration is multiplication where one of the factors is continuously variable. So we want to look at an example of that today, where I'm going to ask you to calculate the mass of a region that has variable density. We're going to use mass is equal to density times area because we have a region and not a solid. So our mass is going to be measured in this case, grams. Our mass measured in grams is going to be the density, which is going to be measured in grams per square centimeter. And so our area is going to be in centimeters. It's a region, and so some centimeters are going to be the dx, and some other centimeters are going to be the dy. And together they're going to be the area. If the density is constant throughout the region, I just need to multiply the density by the area of the region. But we're going to play the variable density game. So we're going to give the region variable density. And so this is going to become an integration problem. And we'll integrate the density over the region. This is going to require that we describe the region to the density function, find an antiderivative, and evaluate. In this case, since we're integrating dA, we're going to create a double integral for the region. Any questions? This one translates up pretty easily to functions of 3 variables, where we have a different density at every point in a 3-dimensional solid. So we would have an integral over a solid W dV. Hope you would do the same thing. I just wanted a picture of the region to practice describing it with a double integral. Questions? Comments? Snide remarks? So when you think about questions, when you start to wonder, when are we going to need to know this? Anytime you use multiplication, think about whether one of those factors could end up being continuously variable. If that happens, you're going to be doing integration. You have integration in your future. So make sure you put some mathematicians on your Rolodex. Otherwise, you're going to have to find some antiderivatives. Try to have some problems for y'all to do. I have described the region, and we also have as another feature of this region, I gave you a function that wasn't strictly invertible. You have to think about it a little bit. Fortunately, we didn't think about it in exactly the same way we thought about things yesterday. So in this case, we've got a region R bounded by the x-axis and the graph of the parabola 6x minus x squared. So notice that 6x minus x squared, if we have to describe this with a dy, or if we have to describe this as a function of y, we're going to have to do a little bit of work to rewrite this function. I know we're all opposed to doing work. That's just a product of evolution. And it's the right answer. But notice that in the first part, we're describing the density as it changes dx, 7 minus 0.5x. So the density varies on different vertical slices. Notice that in the second problem, the density varies in different horizontal slices. So the density is 3 plus 0.1 y squared. So the density is varying this way. So what you want to do in each of these problems is write a double integral for the mass of the region. If you are feeling adventurous, you can write 2 double integrals for the mass of the region.